you doing here? I guess it's about time to spring into action. Hopefully, we remember that the vector sum of all forces on an object is equal to the mass of the object times the acceleration of the object. Okay. Now, in the case of a horizontal spring, or a spring that's stretching horizontally in a mass that's sliding along a horizontal surface, to start, we'll say this is frictionless. What we're going to see is that this mass, as it's stretched at that point, would have a force of gravity pulling it down, a pointing up, and then finally it will have a force from the spring. I want you to take a second and think about what direction this spring force comes from. Brilliant! It is pointing that way, toward the equilibrium point. What is the magnitude of this force? I'm going to consider the magnitude of this force to be based on Hooke's law for a linear spring, which is to say the force of the spring exerted by the spring on the mass is equal to the negative of kx, x being the displacement direction. In this case, the x would be negative. And so the force by the spring would be in the positive direction to the right. That's what that negative takes care of right there. If x is negative, the force is positive. If x is positive, the force is negative. Negative being a directional value. Okay, this k is the spring constant. And the unit is in newtons per meter. How many newtons of force does it take to stretch each meter of the spring? Strings are different. Okay, so this should be at this point review. It should also be review to consider that the potential energy stored in the spring is equal to integral of the force of the spring exerts across a distance. And if we are to look at this pretty carefully, what we'll notice is that we get mu s equals just the integral of kx, because we get some negatives canceling out here, and that's equal to 1/2 kx squared plus c, but here we're going to say over the full length of displacement from 0 to x, and we'll say this is big X there. And so what we get in the end is an expression for the potential energy stored in the spring based on the amount of based on the change in position of the spring and the force it exerts across that distance. Okay, so we have this potential energy value for the spring, and that's the energy stored in the spring. And we want to know how that's going to affect this mass as it moves. Now, let's think about this for a second. In order to check out the energy of this object, this mass, well, what types of energy does it have? Does it have gravitational potential energy that we care about? Not really. Does it have kinetic energy? Well, it depends. all the way out here, it will have none. If it's stopped all the way out here, it will have none. If it's stopped at any point, in fact, it will have none. But if it is moving, then it certainly does. So if we consider the spring block system, we have both this potential energy value and a kinetic energy value of the block. And those together are the energy of the system. The total energy of the system here v squared plus 1/2 kx squared, and that is on this basic flat plane under this particular situation. When we start talking about springs where we have masses going vertically, we have a different story. If we have friction here, that's a different story. But in the case of a frictionless surface and an ideal linear spring, and all sorts of other fancy spherical cows that we're throwing at this problem, this is a nice relationship that we can have. That at any point, these two values will have to add up to the total energy. Let's take a look at a particular example. Okay. So I'm going to say that I have a mass here on a frictionless surface. That's an L. So I have a frictionless surface, I have a mass, and I attach to it a spring. And I'm going to say that I have, this is my 0 mark, I have stretched it in that direction by 2 meters. I'm going to say that the mass is equal to 5 kilograms. And I'm going to have to actually also give this a value for the spring constant. So I'll say that K is equal to 20 newtons per meter. Okay, and I've stretched this mass out 2 meters, so I'll say that my X value is 2 meters. And so at this point, you can make a good assumption that, okay, well, let's see what the spring force is at that point. I can calculate 1, I'll calculate the force from the spring. 2, I'll calculate the spring potential energy. And then 3, I want to figure out the maximum speed. Consider this, and that will lead us into our next problem. Okay, so force of the spring should be pretty simple. I should be able to calculate here that Fs equals negative Kx, where that's negative 20 newtons per meter times 2 meters is equal to negative 40 newtons. Now, negative 40 newtons, the negative stands for moving or having the force in this picture. That's what the negative stands for there. The force, the spring is pulling this block to the left. I'm holding it here, but there's a 20 Newton force or a 40 Newton force pulling me that way. Okay, now the next thing that we have to consider is, okay, so what's going to happen with the potential energy? Well, very similarly, I can simply calculate it. K of the block is equal to 1/2 mv squared, which is equal to 0 joules at that point. Well, that's the kinetic energy. I said I was finding the potential energy. Let's retry that. We found something interesting but useless for the moment. So just as a kinetic energy is 0 joules at that point. But for the potential energy of the spring, it's 1/2 kx squared, and we can simply calculate that by saying it's 1/2 times 20 newtons per meter times 2 meters squared. And this will get us to 10 newtons per meter times 4 meters squared, which is equal to 40 Newton meters. And 40 Newton meters is equal to 40 joules of energy. Presumably I did that math right, but who knows? You should check it for me. Okay. Now, the next thing I want you to do is, okay, so we've calculated our potential energy, so now we want to find our maximum speed. Well, just as with any conservation of energy problem, our maximum speed is going to be calculated by taking the by just saying, okay, well, what happens when our potential energy goes to 0? But first we want to think about where that is and why that is. Where's our potential energy 0? Well, our potential energy is 0. Our potential energy from the spring is 0, exactly when x is 0. So we know that U S equals 0 at x equals 0. Put some units in there. At 0 meters. 0 joules at 0 meters for potential energy, which means that our kinetic energy at 0 meters has to be equal to 40 joules by conservation of energy. And, well, how are we going to set this up? We're going to say that's equal to 1/2 mv squared, which is equal to 1/2 times 5 kilograms times v squared. So I'm going to erase this down here. Maybe I can do this slightly differently. Now, what we're going to do is we're going to simplify this. And we get 40 times 2 equals 5v squared. Divide by 5, so I get 80 over 5 equals v squared, which, if I remember correctly, that's some number. What is that, 16? 16 equals v squared. So v is equal to, yes, you're right, 4 meters per second. And if I didn't make any rookie mistakes there, we'll see how that went. You should be tracing the units as you move through this. That's joules, which is Newton meters. That's a scalar value that which is unitless, or rather, this is a unitless value. That is a kilogram value. Divide by kilograms. Well, newtons is some stuff, so do the conversion yourself at this point. Okay, so we have 4 meters per second as my maximum speed. That's assuming that I have no potential energy at this point. Well, why don't I have potential energy at that point? My force is 0 at that point. And if potential energy is based on the speed or the force applied across the distance, well, I have no force there, so I have no potential energy. In fact, my acceleration at that point is 0. Here, my acceleration moves me to the left. Here, my acceleration moves me to the right. And in this case, I'm speeding up that way. And then in this case, I'm slowing down as I come here. And then I'm going to start speeding up this way and then slowing down. And so this is going to actually be a cycle where we go between 0 meters per second on the very edges and 4 meters per second in the very center in this back and forth motion, this oscillatory motion. And there are all sorts of words we can use to describe the math behind this, and whether we have friction or not, or whether there's some damping force of another kind. We can really take a look at some differential equations there. But one of the things that's really very interesting is how we can actually pull information about the speed and motion of this block straight from Newton's laws and Hooke's law. And that's where we're going to go from here.